Organic Chemistry, Chem 212, Exam 4, Part 2 material. On the previous video, we started learning about R and S, and now we're looking at R and S in Fischer projections. I do have two different molecules here. I want you to look at the bond lines though, and that's what we're checking out here. When you have a carbon in a Fischer projection, the horizontal bonds here are always coming out at you. Do you see here we also have them coming out at you? And this vertical bond up at the top is going behind. The carbon-carbon bond is in the plane of the paper or the slide here, and this one is going behind. So on this example, I do have different things on here. I have a COOH group. This is a carboxylic acid group. This is going back. This carbon and this carbon are in the same plane as each other. The horizontal is coming out at me, this is coming out at me, and again, this one's going back. When the lowest priority is on a vertical bond, pointing away from you, then you simply examine the direction of the priority of the other three groups from the highest to lowest. Remember, the top is back, the bottom is back, and the horizontal lines are coming out. This CH3 is going back, this OH and the CH3 is coming out at me, and this H is going back. That means the lowest priority is away from me in this Fischer projection. Fischer projections are basically going to be using these flat lines, but we understand that there's three-dimensional feature to it. Since hydrogen, the lowest priority, is on a vertical, meaning it's going away from us, it's the direction that we observe. So we have oxygen will be number 1, this carbon with its oxygens number 2, and this is number 3. Notice this is going in an R direction. This is an R molecule. So the advantage of a Fischer projection is we can still show three-dimensional structure or the spatial orientation without having to draw all those wedges. So my lowest priority is on a vertical, so it's what I see. This is number 1, this is number 2, this is number 3. The direction is counterclockwise. This would be an S. When the lowest priority group is on a horizontal bond, that means it's pointing towards you. So the lowest priority is towards us. That's the opposite of what you want. So that means it's the opposite of what we observe. We're looking at the wrong side of it. We look at the direction of the priority of the three groups. Lowest priority is on a horizontal. It's the opposite of what it appears. We know that this is number 1, this is number 2, and this is number 3. So it appears to be going in counterclockwise. Because hydrogen is on the horizontal, it's the opposite of what we see. So it's not an S, it's actually an R. So I have 3 different molecules here. I want to know which ones are the same as each other, and if one of them is different, then you're going to label that as being an enantiomer. All of these chiral molecules have the 4 different same things. They're the same as each other, but are they enantiomers of each other or different? Remember, if the lowest priority, in this case hydrogen, is on the vertical, it's what you see. If the lowest priority, in this case again hydrogen, is on the horizontal, it's opposite of what you see. Go ahead and rank these as R or S. Pause the video, come back and check your work. A and B are both R. Now with A, the lowest priority is on the vertical, so it's what I see. On B, the lowest priority is on a horizontal, so it's the opposite of the direction that it's written. Remember, the lowest priority is towards me, and it's supposed to be away from me, so that's an R. And then C is an S, because again, the H is on the horizontal, so it's the opposite of what you see. So that means A and B are the same as each other because they're R. Now S would be the enantiomer of A and B. A and B are the same. C is an enantiomer. Diastereomers. These are stereoisomers that are not mirror images of each other. The chiral diastereomers have one opposite configuration at one or more chiral center, and the same configuration at others. Here we have an example of 2 molecules where there's more than one chiral center, so we're going to get some practice with that. Again, this being a Fischer projection, anything on the horizontal is coming at you, and the verticals on the ends are going away from you. Assign R or S to each chiral center. I'll do the first one with you, and then you can pause the video and do the second one and check your work. So we know this is a chiral center. This would be number 4. Nitrogen would be number 1. Carbon to carbon, carbon to carbon. Okay, there's a tie. So how do we break the tie? This carbon has 3 bonds to oxygen, because remember, one of those is double bonded. This carbon has only 1 bond to oxygen, so this would be a higher priority. This would be 2, and this bond would be 3. Because the hydrogen, the lowest priority, is on the horizontal, it's the opposite of what I see. So I see this going as counterclockwise. So this one right here is actually an R. Now looking at this one down here, I have lowest priority 4. Oxygen is going to be number 1. And then I have a carbon this direction with just hydrogens and a carbon with a bunch more stuff on it. So this one's going to be lower priority. So this is going to be a 3, which makes this a 2. So you might want to go ahead and somehow note that these are different from each other. Because the lowest priority is on the horizontal, it's the opposite of what I see. So I see 1, 2, 3. I see it going as S, but it's the opposite. So this is actually an R. So I'm going to go ahead and clean this up. I don't know if you want to pause the video and take a look at these numbers again, but I'm going to pause the video and go ahead and get rid of these numbers and put the R or S in here. And then you can go ahead and do the same thing to this one on the right. All right, I went ahead and did the priorities on this top one here. I have the lowest priority on the horizontal, so it's the opposite of what I see. I see it going counterclockwise, so this one would be R. And on this one, the lowest priority, again, is on the horizontal. It's the opposite of what I see. This appears to be an R, but it's actually an S. When we have more than one chiral center, when we have the name, we don't just put an R or S in front of the name. We have to say which atom, which carbon we're talking about that has the R or the S. And again, they may not be the same as each other. So what you're going to do is you're going to look at this molecule and you're going to count down. This would be carbon number 1. And working our way down, this would be carbon number 4. That makes this carbon here a 2R. That's where this came from. Coming down, this would be a third carbon, so this would be a 3R. On this one, here's carbon 1. Here's carbon 2, 3, and 4. So again, working down, I have a 2R and a 3S. So this is what we'll be putting in front of the names when we have more than one chiral center. This slide is talking about diastereomers, so what that means is we have one chiral center that's the same as the other, and in this case, our 2R is the same as each other. That's why these are diastereomers of each other. So in the previous slide, we saw diastereomers can have one chiral center the same as each other. When you have enantiomers, they're at opposite configurations at all chiral centers. You can see this one is 2R, 3R, and this one is 2S, 3S, so they're different. You might want to go ahead and pause the video, rank these, and convince yourself that this is an R and this is an R, and then practice this is an S and this is an S. Meso compounds. Meso compounds are achiral, yet they have chiral centers. But what keeps them from being optically active is they have a plane of symmetry. And here we have a great example here. Right in the middle of this molecule, we have a plane of symmetry where the top and the bottom are mirror images. So these are achiral. In this case, they're showing you, these are meso compounds, but they're also showing us that they're identical to each other. So we have the meso piece that makes them achiral because we can go ahead and cut them right there in the middle, and that's where the plane of symmetry is. But what they're describing here is if you were to take this molecule and flip it 180 degrees, even though you have 2R3S, this is the same exact molecule. Looking at it from top to bottom, this would be 2S3R. This is the same molecule as each other. So they're using a meso example to show you that you can actually draw the same compound 2 ways. Molecules with more than 2 chirality centers. Molecules can have very many chiral centers. Each point has 2 possible permanent arrangements, either R or S, generating 2 possible stereoisomers. So the number of possible stereoisomers with n chirality center is equal to 2 to the nth power. Cholesterol has 8 chiral centers. meaning that there are 256 stereoisomers, but only one is produced in nature. This is the structure of cholesterol, and the asterisks show you the locations of all the chirality centers. This is a molecule of ephedrine. Find the chirality centers, and then using 2 to the nth power, how many stereoisomers are possible? Well, anytime we have a carbon-carbon double bond, those two sides will be the same. This has 4 different groups. What group is not shown in this line structure is a hydrogen. Same thing here. There's a hydrogen here that's not being shown. So this has 2 chiral centers. How many stereoisomers are possible? 4. Physical properties of stereoisomers. Enantiometric molecules differ in the direction which they rotate plane polarized light, but their other common physical properties are the same. Now, diastereomers have a completely different set of physical properties. This table shows us some properties of the stereoisomers of tartaric acid. The plus, which is the R, rotates plane polarized light plus 12 degrees, while the S, indicated as minus here, same number, but a different value. They both have the same melting point as each other, the same density, and the same solubility. Now the meso form of this does not rotate plane polarized light because it has that plane of symmetry in the middle of it, and you see it has a totally different melting point, density, and solubility. Racemic mixtures and their resolution. Racemic mixtures, or racemate, is a 50-50 mixture of 2 enantiomers, the positive and negative, or the R and the S. In order to get a pure compound, they need to be separated from each other or resolved from the mixture using an acid-base reaction. The way racemic mixtures are written is you can have a plus-minus sign in front of the name, or you can use a D and an L in front of the name. The D and L can be uppercase or lowercase, and we can also use R and S. Racemic mixtures and individual diastereomers differ in physical properties such as solubility, melting point, and boiling point. Stereochemistry of reactions. In this reaction, where we add HBr across a double bond, we can see that our product can be chiral. So we can start off with an achiral molecule, have it undergo a reaction, and it becomes chiral. Our example here is adding HBr across the double bond of 1-butene, and then we get a chiral carbon at the second carbon in. We get a racemic mixture, we get both, that's why there's a plus and minus here. So the name of this compound would be plus minus 2-bromobutane, 2 because bromo is coming off carbon number 2. The reason why we get both, the plus and the minus version, is because this reaction happens via a carbocation, where both the top and the bottom, when the carbocation is formed, are equally accessible. The transition states are mirror images, and the product is racemic. Stereochemistry reactions, addition of Br to alkenes. We're going to be looking at some stereo-specific reactions. In this case, cis forms a racemic mixture. The brominium ion attacks on both carbons equally from the top side or the bottom side. It's an anti-addition. So we're going to get a racemic mixture. Here we have an example of a name 2. Take a look at this, 2s,3s dibromobutane. So before we were talking about numbering from top to bottom. In this case, you would number them from left to right if you see them going sideways like this. So this one we have a 2r, 3r dibromobutane. These are going to be a racemic mixture because we have differences. These are enantiomers. We have different orientation at all chiral centers. Now, when we start off with trans-2-butene, we actually get a meso product. Both products can either come from the top side or the bottom side, so these are not going to be optically active because they're meso. Again, take a look. You might want to practice your nomenclature. You can see the nomenclature of this compound and this compound. Stereochemistry of reactions, looking at the addition of HBr to a chiral alkene. If one or both reactants are optically active, the product can also be optically active. This gives diastereomers in unequal amounts due to the steric reasons on the attack of the intermediate. Here we have a carbocation. In fact, this is a secondary carbocation, and bromine can either come from the top or the bottom here. On the bottom attack, we actually get one of the diastereomers. Notice the 4R is the same in this case versus the 4R in this case. But what's different is we have a 2S and this is a 2R. Now this says we get diastereomers in unequal amounts due to steric reasons. This has to do with, can this bromide do the top side or bottom side attack? If there's stuff in the way, that means it's sterically in the way, so that would be the steric reason. So if they indicate there's steric reasons, physically something is in the way. Now we've been talking about chirality on carbon, but we can have other atoms than carbon show chirality. Silicon, nitrogen, phosphorus, and sulfur can be chiral when they're tetrahedral and have 4 different groups. Now when nitrogen is bonded to 3 groups, nitrogen is tetrahedral and the lone pair of electrons is considered a different group. But it doesn't form a chiral center because it rapidly inconverts back and forth and back and forth. It's almost like an umbrella going back and forth and back and forth. It happens so fast that they're both present at the same time, or at least it seems like they're both present at the same time, so it doesn't show optical activity. Now this can also apply to phosphorus, but phosphorus flips more slowly. Organic Chemistry 212, Exam 4 Material, Part 3. Alkyl halides. We've included halogens in our compounds already, so now we're going to get a little more specific on alkyl halides. So some of this might be refresher or review, and some stuff might be new. What is an alkyl halide? It's an organic compound containing at least one carbon-halogen bond. X typically represents a halogen generically, so F, Cl, Br, and I all have opportunity to do a single bond. So for our organic compound, it usually replaces the location of a hydrogen. An alkyl halide can contain many carbon-halogen bonds. Properties and some uses. We have fire-resistant solvents, refrigerants, and pharmaceuticals and precursors. This is a drawing here of dichloro-difluoromethane. It's a refrigerant. Naming alkyl halides. Well, you've already been doing this before, and alkyl halides are really low on the priority list. In fact, double and triple bonds have higher priority, and don't forget that they determine the numbering system. So when we're looking at this, you're going to, if it doesn't have a double or triple bond, you're going to name it just as we did the other alkanes. You look at from one end of the molecule and see where the first substituent comes off, whatever direction gives you the lowest composite number, that's the way you're going to go. Now, if you have more than one of the same thing, just like you did with methyls and ethyls, you use the prefix di, tri, and tetra. If there are several different halogens, you list them in alphabetical order. Here we have a list for some commonly and widely used names for alkyl halides. You do want to know these. Chloroform is a single carbon with 3 chlorides on it. Carbon tetrachloride, again a single carbon but 4 chlorides on it this time. Methylene chloride, 2 chlorines on there. And methyl iodide, a carbon with 1 iodide. Draw the following. Go ahead and pause the video, come back, and see how you did. 2-iodo-3,3-dimethylhexane. I actually wanted to purposely use this font here. Do you see this iodine here? It doesn't have the top and bottom. It's sans serif. What's going to happen is it looks like this is just a bond line broken, but you need to get familiar with knowing that this is going to be an iodine, even though it doesn't have the top and the bottom on it. So I wanted to show you an example like that so you'd be familiar with this format. Letter B, we have 3-chloro-3-ethylpentane. And number 4, 3,3-dibromo-2-methylhexane. How'd you do? Name the following. And I have let's take a look here. Letter B and letter E have multiple bonds in there. Don't forget the multiple bonds have priority over any of these substituents that we have so far, halogens or alkyl groups. Go ahead and pause the video, come back and see how you did. All right, longest continuous chain regardless if it bends and curves. I have 7, that's heptane. I have something coming off from left to right on carbon 2, then 3, then 4. And in the opposite direction, I have something coming off of 2, but the next one doesn't happen for a while. So breaking the tie means it goes in this direction here. 3,4-dibromo 2,6-dimethylheptane. When you write the name, don't forget that numbers and numbers are separated by commas, numbers and letters are separated by dashes, and yes, they're extremely important to be there. Be sure to include them. On letter B, longest continuous chain, which contains that double bond here. Because the double bond's nearer to this end, this means double bond starting on 2. That means my iodine is actually on carbon number 5. So that'd be 5-iodo. 5-iodo 2-hexene. Longest continuous chain on C has 6 carbons. Now the direction would be left or right because I have 2 things of coming off carbon number 2 going in that direction, but only 1 thing coming in the opposite direction. 2-bromo 4-chloro 2,5-dimethylhexane. This bromo, because it's alphabetically before chloro, which is C is alphabetical before M for methyl. Remember, the prefixes aren't included when we figure out the order. Letter D, you need to find the simplest way to name it. In this case, we have to have our longest chain include this bromo. That means this is going to be an ethyl group. So the name of this one would be 1-bromo 2-ethylpentane. All right, I want you to see this. This is a chloro, not a carbon. This is another formatting issue where if we were to be very quick, we might mistaken this for a carbon. So our longest continuous chain, which contains the whole triple bond, is right here. So I have a chloro coming off of here and a bromo. Triple bond has priority, so this right here happens to be carbon number 2. So my triple bond is starting on carbon number 2. That means bromo, my substituent bromo, is going to be a 1-bromo because the triple bond told me the direction is this way, and that means my chloro is going to be a 6-chloro. Now remember, this is carbon number 6 here. Remember, we list them alphabetically. We determine where they are physically, and that's when we establish the numbers. But we list them alphabetically. So bromo, chloro, and this 2 tells me where the triple bond is. How'd you do? Structure of alkyl halides. They're sp3 hybridized, and the carbon-halogen bond is longer and weaker as you go down the periodic table. The carbon-halogen bond is polarized with a slight positive on carbon and a slight negative on the halogens. That would make this carbon an electrophilic carbon. That means it's electron-loving because it's positively charged. It's attracted to electrons. So how do you make alkyl halides? Well, 2 reactions we've already seen in section 7.2 and 6.8. We can form an alkyl dihalide from an anti-addition of bromine or chlorine. That would be this example coming to the left here, an addition reaction across the double bond, and it's anti. We can also form it with the additional reaction of HCl, HBr, HI to alkenes, giving us the Markovnikov product, and this was covered in section 6.8. So for more details on those reactions, on everything that's required on the reaction conditions, be sure to look back at those. Another way to prepare alkyl halides comes way back at the beginning when we talked about radical substitution reactions in section 5.3. This requires 3 steps: the initiation step to form the radical, propagation step, which is a repeating cycle, and the termination step that ends it. This is a pore synthetic method. In the radical halogenation, you can only add 1 halogen at a time. And some of the drawbacks or limitations is it's kind of hard to control, and it's really not a good idea to plan this as a synthesis method. So yes, you can make an alkyl halide this way, not the best method. And we can also see on the next slide another reason why it's not so good. When we have a radical halogenation of alkanes, we can also get more than one product. If there is more than one type of hydrogen in an alkane, the reactions favor replacing the hydrogen at the more highly substituted carbon, but this isn't absolute. If we take a look at this reaction of 2-methylpropane with chlorine, we have, looking at this molecule, we have 3 different sets of hydrogens that are identical to each other. In fact, these 9 hydrogens are identical, so we can substitute on here a halogen for a hydrogen. But we also have a second type of hydrogen, and that's one here. And that means we'll get 2 products out of this. So one of the reasons why this is not a very good way to make an alkyl halide is because we have too many products possible. Relative reactivity. Based on quantitative analysis of reaction products, the relative reactivity has been estimated. This order parallels the stability of radicals. Reaction distinction is more selective with bromine than chlorine. Reactivity of hydrogens. The most reactive hydrogen is when you have the most R groups. When you have 2 R groups, it's not as reactive, and primary is the least. So this table that they're showing you is they're showing you relative reactivity. So for every primary carbon that reacts, 5 tertiaries react. We also see that when the radicals are there, that the tertiary, the 3 R groups, is going to be more stable than the primary. The more R groups you have, the more stable it is. So I have a problem here. I just want a monochlorination. Just put 1 chlorine on here. But I like this example because you're going to see one of the limitations we have with this radical reaction is you get so many products possible. So take a really close look at my reactant and find out how many monochlorination products are possible. Now we're going to ignore any of the stereoisomers. We're just going to go straightforward monochlorination. Go ahead and pause the video, find out how many of these you can find, and let's check your work. There are 4 possible products from the monochlorination of methylcyclopentane, ignoring stereoisomers. This N carbon here can get a chlorine on it. Coming in 1 carbon over to the left, this does have a hydrogen. It's a line structure, so you may not have recognized that. This is a spot where a chlorine can go. And then 1 away from that, that would be this one, is where a chlorine can go. And 2 away from that is where another one can go. If we continued around the ring, we'd start repeating. Continuing on with more reactions of how we can get a halogen on there, let's look at the allylic bromination of alkenes. NBS. That's its abbreviation, and typically that's what you would see over the reaction arrow. N-bromosuccinimide. It selectively brominates allylic positions. That's the carbon next door to the double bond. I liked this drawing here to show us the difference between the vinyl position, the allylic position, and what's just a plain old alkyl position. When you have a carbon-carbon double bond, the carbon involved in the carbon-carbon double bond attached to that would be the vinyl position. 1 carbon away from the carbon-carbon double bond is the allylic position. This is a reaction where this allylic hydrogen is where the bromine's going to go. Here's a general reaction. I don't have anything on the ends of these because they can pretty much be any kind of R group, but it's this hydrogen here that in these conditions using NBS, light, and CCl4, where the bromine doesn't add across the double bond. Take a look. It attaches or actually substitutes on the allylic position. If you want to know what NBS looks like, what its structure is, this is its structure here. You might want to add that to your group of functional groups that you need to know. But when you write the reaction, just simply put NBS over the arrow, but don't forget to put our HNU and CCl4. So now that we've added the allylic piece, let's take a look at a more expanded stability of radicals. And not only do we have the allylic position, but we have the vinyl position there. The least stable is the vinyl position when it's in its radical form. As we've seen earlier, we have methyl, then increasing in stability is a primary, secondary and tertiary. But now, more stable than a tertiary is the allylic position. Why is the allyl radical more stable? It's because of resonance. 3 electrons are delocalized over 3 carbons. And what that does is it causes, an attachment between these guys, so it's held together very well. Here is a resonance arrow showing us that the double bond could be left of center or right of center, and notice the radical is switching back and forth and back and forth.